All right, well, let's get into it. Today, we're popping the hood on AI vision. We're going to explore the actual blueprints, the designs that finally taught computers how to see.
So, you've probably wondered, how in the world did we teach a computer to tell a cat from a dog? I mean, it's the classic question, right? For the longest time, it felt totally impossible. And the big secret, the huge breakthrough, wasn't what you might think. It wasn't just about throwing more and more data at the problem.
Nope. The real revolution, the game changer, was in the design. It was all about building a better blueprint for the AI's brain, the architecture itself. That's what unlocked everything. That was the secret. Okay, so to really get how we got here, we got to go back, way back, to the very beginning, to the model that first showed everyone, hey, this might actually be possible. And here it is, LuNet 5, all the way from 1998. Now, its job was pretty specific, reading handwritten numbers on bank checks. You can totally think of it as the granddaddy of all modern vision AIs. It introduced these two killer ideas. First, convolutions, which are like these little detective filters that scan the image for basic stuff like edges and curves. And second, subsampling, which is a clever way of shrinking the image down to focus only on the most important bits. This thing was the proof of concept. It showed the world that this whole approach could actually work. So for more than 10 years after LuNet 5, things kind of ticked along. Progress was happening, but it was slow. And then, 2012. Everything changed. I mean, everything. It was like a big bang moment for deep learning, and it was all because of a brand new and way, way bigger blueprint. Just look at this. This visual says it all. On the left, you've got the clean, simple design of LuNet 5. And on the right, that's AlexNet. It's a beast. We're not talking about a small step up here. This was a monumental leap in complexity. It wasn't an upgrade. It felt like a whole new species of network, one that could learn things that were way more complex. And the proof is right here in the numbers. See, there was this competition called the ImageNet Challenge, basically the Olympics for computer vision. Before 2012, the top models were stuck with an error rate over 26%. Not bad, but not great. Then AlexNet came along and just demolished the record. It dropped the error rate all the way down to 15.3%. That was it. The deep learning revolution was on. So, what was the secret sauce here? What made AlexNet so special? Well, for one, it was huge. 60 million parameters. It also brought in this thing called the ReLU activation function. It's a simple little trick, but it let the network learn way faster by keeping the learning signals flowing. And, critically, it was built to run on gaming GPUs, which was a total game changer for computing power. Oh, and one last thing. It used a ton of data augmentation, flipping images, cropping them, to basically teach the network what a cat looks like from all sorts of different angles. Okay, so after AlexNet blew the doors off, the race was on. Everyone was asking the same question. What's next? How do we top this? And pretty quickly, two different schools of thought popped up. You could call it a battle between brains and brawn. First up, in the brawn corner, we have VGGNet. The philosophy here was super straightforward. If deep is good, then deeper must be better, right? So the designers just took this one simple, elegant building block, a 3x3 convolution, and just stacked them again and again up to 19 layers deep. It was a pure brute force method, and you know what? It worked incredibly well. Then, in the brains corner, you've got GoogleNet. Their motto was basically smarter, not harder. So instead of just stacking layers endlessly, they created these really clever things called inception modules. Think of it like this. These modules would look at the image using different sized filters all at the same time, in parallel, and then cherry pick the most useful features to pass on. And the result? A much, much more computationally efficient design. So the 2014 competition turned into this epic showdown. You had VGGNet and GoogleNet going head-to-head. And guess what? They both completely shattered the old records. GoogleNet ended up winning, but only by a razor-thin margin. And this was huge because it proved there wasn't just one right way to do things. The brawn of just going deeper and the brains of a more efficient design were both totally valid. It's a design trade-off that researchers still wrestle with today. But there was a problem brewing. That whole deeper is always better idea, it was about to smack right into a brick wall. Researchers started running into this really weird, really frustrating issue that was stopping them from making their networks truly massive. I mean, it seems like the obvious next step, doesn't it? If 19 layers are great, why not try 50? Or 100? Heck,
Why not just build a 1,000-layer network and call it a day? Problem solved, right?
Well, not exactly. And here's the bizarre twist. They found that just adding more layers could actually make the network perform worse. Look at this graph. A 56-layer network is doing worse than a 20-layer one. How is that possible? The culprit was something called the vanishing gradient. Okay, so think of the gradient as the learning signal that gets passed backwards with the network during training. The problem was, when the network got too deep, that signal would get weaker and weaker until it just vanished. It faded to nothing by the time it got back to the early layers, which meant those layers just stopped learning anything. And then it came the solution. It was from a network called ResNet, and it was just breathtakingly clever. Okay, on the left, you see a normal block of layers, but on the right, that's a residual block. See that little curved arrow? That's the magic trick. It's a shortcut connection. It literally acts like an information highway, letting the learning signal just skip past a couple of layers and continue on, full strength, to the deeper parts of the network. That one simple idea, that shortcut, it completely solved the vanishing gradient problem. It just fixed it. And that meant researchers could suddenly build ultra-deep networks. And the result was ResNet. At an absolutely mind-boggling 152 layers deep, it just dominated the 2015 competition. Its error rate dropped to a mere 3.6%. We're talking performance that was starting to get better than humans. So, once the depth problem was cracked, the whole focus of AI architecture design kind of shifted again. It wasn't just about chasing accuracy at all costs anymore. Now, the new game was a balancing act. It was all about performance versus efficiency. And this chart just perfectly lays out the modern design world. So let's break it down. The vertical axis is accuracy, so higher is better. The horizontal axis is computational cost, how much processing power it needs, so further to the left is better. And the size of each bubble, that tells you how many parameters it has, basically how much memory it takes up. The dream, the holy grail, is to be in that top left corner with the smallest bubble possible. All right, let's look at some examples. First up, VGG. Its accuracy is pretty good, right? But look where it is, way over on the right with a giant bubble. That means it takes a ton of computer power and has a staggering 138 million parameters. It's the gas guzzler of the bunch. Yeah, it's powerful, but man, is it expensive to run. Okay, now let's find GoogleNet. See how different that is? It's way more efficient. It gets almost the exact same accuracy as VGG, but it's much further to the left, and its bubble is way smaller. That brilliant inception design meant it only needed about 5 million parameters, a fantastic lean and mean alternative. And finally, let's look at the ResNet family. See them? They're pushed way up there into that top left area, getting the best accuracy on the chart. Now, they aren't quite as cheap to run as GoogleNet, but they offer this incredible balance of absolute top-tier performance for a pretty reasonable cost. And that's exactly why ResNet became the new gold standard for so many different jobs. What a wild ride, right? When you lay it all out, it's incredible. We start with LeanNet in '98, just proving it could be done, then AlexNet's big bang in 2012 that changed everything, then that awesome 2014 race between VGG's brute force and GoogleNet's clever design, and finally, ResNet's elegant fix for the depth problem in 2015. You know, progress got so fast, so good, that by 2017, they actually retired that big competition. The blueprints, the models, had just gotten too good. But I want to leave you with one last thought. Every single one of these amazing, revolutionary blueprints, they were all designed by people, by clever, hardworking human researchers. But the new frontier? It's something called neural architecture search, where we're now using AI to design other AIs, to automatically discover new and better blueprints. And that just makes you wonder, right? What happens when the student finally becomes the master architect?